go ahead and do some of these guided practice problems for these thermochemical equations, all right? So something we'll want to keep in mind is that in this particular thermochemical equation, we notice that the reactants have the energy. What that means is that this is going to be an endothermic reaction. So when the reactants when the energy is in the reactant side, that means that it requires energy for this to proceed. Now, when you go from moles of substance, in this situation, it's giving us 2.25 moles of this, and it's asking for the kilojoules of this, it's just like going mole to mole. It's exactly like that. You just use these coefficients right here. I'm going to call it coefficient to go from one to the next. So we have 2.25 moles of NaHCO3, and we can go from moles to kilojoules using the coefficients there. So the coefficient of NaHCO3 is 2, and the coefficient of the kilojoules is 85. And all we need to do is type that in the calculator, and that will give us the answer to this first problem. And what you end up with is 95.6 kilojoules of energy, and it's got 3 sig figs because we're starting with 3 sig figs, we'll end with 3 sig figs. Now my question is this a positive or negative kilojoules? So this would be a positive because it's absorbing this energy, and so this is a positive change in energy. This next one here, if you take a look, it's giving us the delta H outside of the thermochemical equation, and so it's, and in fact, this is not a thermochemical equation because it does not have the kilojoules within it. Because this is negative, what that means is that this is releasing energy. And so because it's releasing energy, it is going to be exothermic. So because it's negative, it's exothermic. So just to recap on this one here, we knew that it was endothermic because the kilojoules were on the reactant side. If they were on the product side, it would have been exothermic. In this situation, because the kilojoules are negative, right here, because the delta H is negative, that means that it is exothermic. All right, so this question says that we have 12.5 grams of the ethanol, which is the C2H6O, and it's asking how many kilojoules of this will be produced. All right, so what we do is we take our grams, and we can go from grams to moles, because once we know the moles, we can then go from moles to kilojoules, just like we go moles to moles. And so this is grams of C2H6O, and this is moles of C2H6O. And then what we can do is we can go moles of C2H6O to kilojoules. Now, when we go moles to kilojoules, right here, we can just use the coefficients in the equation here. And so notice how this has a coefficient of 1. And notice how this here would be the coefficient of the kilojoules. So it's negative 1368. Now, when we go between grams and moles, we just use the molar mass. So 1 mole of this is going to be whatever that is added together, which gives you 46.068. And so now all we need to do is type this in our calculator, and that will give us the amount of kilojoules that's being released or being produced. And what you end up with is you end up with negative 371 kilojoules of energy being released. And that is your answer. All right, this next one. This next one is asking how much propane, so it's asking the mass of the propane, must be burned to release this many kilojoules of energy. So the first thing we need to do is we do need to write a balanced chemical equation. And so we want to write a thermochemical equation. So the first thing we're going to do is write a balanced chemical equation. So we have C3H8, and this is going to react with oxygen gas because all combustion reacts with oxygen gas. And all combustion has oxygen gas as a reactant. And it will always produce water plus carbon dioxide. And to balance this, we always save the oxygen for last. So we're going to put a 3 here to balance the carbon. We're going to put a 4 here to balance the hydrogen. And then to balance the oxygens, you'll see that you have 4 oxygen right there. You also have 6 oxygen right there for a total of 10 oxygens altogether. So to balance that, you put a 5 right here. Now, to write a proper thermochemical equation, we need to actually include this quantity within the thermochemical equation. So my question is, do we add it to the reactant side or do we add it to the product side? Because it's a negative, that means we add it to the product side. If this were a positive, we would add it to the reactant side. But because it's negative, that means it's being produced. And so let's go ahead and add that. So we're going to put it over here. Kilojoules of energy. However, I made a mistake. And what I want you to do is I want you to pause the video and I want you to see the mistake that I made. So even though this is a negative, when we write a thermochemical equation, we do not say negative 2220. Instead, we say plus 2220. All this negative does here is tell us if it's in the product side or reactant side, but we still say plus that many kilojoules are being released. So make sure that you don't make that mistake. Okay, so in this situation, this particular problem is giving us this right here. It's giving us 5,550 kilojoules of energy. It's saying that we need to produce that much. So we want to produce this many kilojoules of energy, and it's asking how many grams of this do we need. And so we can just go from kilojoules, we can take our kilojoules and we can convert it to moles, right? Because we can go from kilojoules to moles using the coefficients, and then we can just go from moles to grams. And so let's go ahead and do that. So we have 5,550 kilojoules. We're going to go from kilojoules of energy to moles of energy. Then we're going to go moles of energy to grams of energy. When we go kilojoules to moles, we use the coefficients. Here's the coefficient for kilojoules, 2220. And this is a negative 2220. And we know that the coefficient of this is 1. And then we can go moles to grams using the molar mass of the propane. So 1 mole is whatever the molar mass of that is. And that is going to be 44.094. So all we have to do is type this in our calculator. And what we end up getting is negative 110, and we'll do a decimal for sig figs, grams of C3H8. Now, what I'll say is, does it make sense that this is a negative? The answer is no, it does not. It does not make sense that you have a negative grams. So how is it that we're getting a negative? Well, the reason why we're getting a negative is because we're forgetting that this value is actually negative as well. And the way we know that is when you read problem 6, look at this word right here. What does this word tell us about those kilojoules? If it's being released, that means it's losing that many kilojoules, which suggests that it's a negative. And so because you have a negative here and you have a negative here, those end up canceling out. to where you actually get a positive. All right. So this is a different page now. It's a different practice problem. So we're going to be doing this guided practice problems on the next set of notes. And so what we're going to do is we're going to talk about how can we calculate the delta H of a reaction using the heats of formation. All right. And so let's talk about what heats of formation mean. So when we have this right here, let's go ahead and take this as an example. What the heat of formation is, it tells us how much energy is released or absorbed when two elements in their elemental form come together to make that substance. So for example, what this number is telling us, it's telling us that if we had elemental carbon plus elemental oxygen gas, when these two things come together, it's going to make carbon dioxide like this. And when that happens, it also releases this much kilojoules of energy. Now, the reason why we know that it releases that is because this is a negative, and that's telling us so. Let's talk about this one above, though. This one, what it's saying is that if we had carbon plus hydrogen gas, and we form this right here, for the elements of this compound to come together to make this compound, there's a 3 and a 3 here, this will actually absorb it'll actually absorb this much energy. And the reason why we know that it absorbs that much energy is because this is a positive heat of formation, is a positive delta H. So you can see that when elements come together to make a particular compound, it will either give off a certain amount of energy or it'll absorb a certain amount of energy, and that's what these heats of formation tell us. So here's a couple more examples. You can see that when these elements come together to make this, what ends up happening is that it's going to release this much energy. So the heat of formation for this particular substance is this. Now, I do want to highlight something about this one right here. This one, if you take a look, this equation is not balanced. And to balance this, you may think that you need to put a 3 here and a 2 here. However, the definition of the heat of formation of a substance states that it's the heat that is released or absorbed when 1 mole of substance is formed. And so this always has to have a coefficient of 1 when we're talking about the heats of formation. So the only way to actually balance this equation while keeping this a 1 is to put a fraction here, 3/2, to balance this particular equation. And so you will see this right here, you will see a fraction, or you can see a fraction within these types of within the heats of formation, showing that the elements come together to make 1 mole, right? So again, the whole idea is that 1 mole is supposed to be produced, and so that's why you can have a fraction when talking about specifically heats of formation. So the way that you calculate the change in enthalpy of a reaction using the heats of formation is by adding up the heats of formation of the products, and then you subtract the heats of formation of the reactants added together. And so what this little symbol means, it means sum. In other words, adding together. And so what we do is we add up the heats of formation of the products, and we subtract the heats of formation of the reactants. And so we can go ahead and take a look at a practice problem here to see how we can calculate the change in enthalpy of a reaction using the heats of formation. All right, so again, the change in enthalpy of a reaction is going to be the sum of the products minus the sum of the reactants, all right? So when we are doing this, we have our products here, and then we subtract our reactants. And so right here, carbon dioxide has a heat of formation of negative 393.5. However, do you want to take a guess what we need to multiply that by? We need to multiply it by 6 because there's 6 carbon dioxides within this balanced chemical equation. So we have this, plus we also have this particular substance as well, water. So we have water as a product there. And so water is going to be negative 286, and we multiply this one by 6. So again, it's the products added together, and so that's what we just did right there. So I'm going to go ahead and put this in bracket because you add all of that together, and this is the products, minus the reactants added together. So if you take a look, we have this one right here, okay? And this happens to be C3H6. We have to multiply this one by 2 because it's got a coefficient of 2, plus whatever the heat of formation of this is. However, this chart right here does not, so this chart right here does not give us the heat of formation of the oxygen gas. And the reason why it does not is because it is an element, and elements have a heat of formation of 0. And that's just the definition of that. So that's just all elements will have a heat of formation of 0. And just to clarify why that is, again, what heats of formation are, it's how much energy is released or absorbed when these elements come together to make the compound. And so we're using elements as the baseline to determine what the change in enthalpy of them coming together is. All right, so now we have reactants added together. So again, we have our products, we add them together, and we take our reactants, add together, and we subtract that. And also, I accidentally wrote the formula here rather than the actual heat of formation of that compound. So here's our products added together, and then we just subtract our reactants added together, and that will give us our answer. Which that will give us negative 4,118 kilojoules of energy. So this reaction has a delta H of negative 4,118. So if we were to write a thermochemical equation, what we would do is we would write this balanced chemical equation, and then we would add 4,118 kilojoules to the product side. And the reason why we know it goes to the product side is because it is negative. If this were positive, it would be on the reactant side. All right, so we're going to move on to number 3, and we're going to talk about energy diagrams. And so you can see that this is an energy diagram, and what it does is it shows us the energy of the reactants and the energy stored within the products. And so what we can do is we can calculate the change in energy of from reactants to products, and we can determine the delta H of the reaction. We can determine if it's endothermic or exothermic. So if we're starting off at 250 and we go up to 300, that is an increase of 50 kilojoules of energy. So the delta H of the reaction is going to be 50 kilojoules of energy. So it's the amount that it goes up. Now, is that a positive or a negative? Well, because it's going from 250 to 300, it is a positive. It is gaining 50, and so this is a positive kilojoules. Because it's a positive kilojoules because it's a positive delta H. That means that is an endothermic reaction. Now this here, you can see starting off at 450, and it's dropping down to 300. So it's going from 450 to 300. And so this is losing 100 kilojoules of energy. So the delta H of this reaction is going to be negative 100 kilojoules of energy. Because it is a negative, it is going to be exothermic. So the last thing that I want to talk about is breaking bonds and forming bonds. And this is a very common misconception. Anytime you break a bond, notice how we have this carbon-hydrogen bond here, and there's no carbon-hydrogen bond over here. So this bond is breaking. This bond is breaking, this bond is breaking, this bond is breaking. And the reason why we know that is because there is a carbon-oxygen single bond here. We also have a carbon-hydrogen single bond there, and there's none of those types of bonds over here. We can also see we have this oxygen-oxygen double bond that is breaking as well. Anytime you break a bond, that is an endothermic process. That requires energy. Energy is absorbed in the breaking of bonds, and that is a common misconception. Because a lot of people think that energy is released when bonds are broken. But the reason why that's wrong is because it's not that energy is released when bonds are broken, it's that energy is released when new bonds are formed. There is energy stored within the bonds, but to break the bonds requires energy. What ends up happening is that when these bonds form, this is actually an exothermic process. So when bonds are formed, energy is released. And so energy is released when the new bonds are formed. And a reaction will be exothermic if the amount of energy released is greater than the amount of energy absorbed. And a reaction will be endothermic if the amount of energy absorbed in the breaking of bonds is greater than the amount of energy released. So from this particular image here, all I want you to take away is that to break bonds requires energy. It's kind of like separating two magnets. These atoms are bonded together and they're attracted to each other. It's going to require energy to break them. And then when new bonds are formed, energy is released. So let's go ahead and talk about energy, how these energy diagrams, how we can see where the bonds are breaking and where they're forming, and how that determines if something's endothermic or exothermic. So again, for bonds to break, you have to add energy into that system. And so that is kind of what this first part represents in this energy diagram. This is the activation energy required to break apart the atoms from each other. Another way of thinking about it is this is part of the, so the bonds breaking is part of the activation energy. Then we have this part right here. This is where bonds are forming. So these are bonds forming. And so you can see that in this situation, the energy required to break the bonds is smaller than the energy released in the forming of bonds. And so in this situation, we have more energy released in the forming of bonds, which is why we end up with an exothermic process. In this situation, though, you can see that this much energy is required to break the bonds. And so this is breaking bonds again. So breaking bonds. And then this part is forming bonds. So same thing as before. However, notice how the amount of energy required to break the bonds is greater than the amount of energy required to form the bonds. And so, or the amount of energy released in forming bonds. And so this is an endothermic process because it requires more energy to break the bonds. So to kind of sum up everything, this particular, this chart is in your book, but an endothermic process breaking bonds is always an endothermic process. Greater magnitude of energy absorbed when bonds are broken will result in an endothermic process. So kind of like this. So it's an endothermic process because there's a greater magnitude of energy absorbed when bonds break. And then you can see that more energy is needed to break the bonds in the reactants than released when new bonds are formed in the products. And so that's exactly here. So you can see there's more energy required to break the bonds. There's less energy released in the forming of bonds. Now, an exothermic process, so forming bonds is always an exothermic process. So whenever bonds are formed, it's exothermic. So this right here is the forming of bonds. There's less energy is required to break bonds in the reactants than released when new bonds are formed in the products. And that's how you end up with an exothermic reaction. So you end up with an exothermic reaction when less energy is needed to break the bonds compared to energy that is released when new bonds are formed. And so that's how you have an endothermic reaction versus an exothermic reaction. And this diagram really helps show this. You can see that we have these right here. They're bonded together, but to break apart those atoms, it requires energy to break them apart. But when they form new bonds, they then release energy. And you can see in this situation, this here it will be an exothermic process because it's releasing more energy. And so we can do plus energy over here. So an overall release in energy will occur.